Hello and welcome. Today we are going to talk about dot products, vectors, and distances between points. So, what are vectors and how they are used in machine learning? In machine learning, they are called feature vectors or parameters. So, what you see in this slide is a column of city, rainfall, and temperature. So here for each city, there are different parameters that are particular to that particular city. For example, city A has rainfall 100 millimeters or 3.93 inches. It has temperature of 30 degrees centigrade or 86 degrees Fahrenheit, and those two parameters describe that particular city. Similarly, for city B, there are different rainfall and temperature. Now, in a data set for such as this one, there will be multiple cities, and each of the city is described by a specific number for rainfall and specific number for temperature. So, how would we group these cities together based on these two given parameters? And that's where feature vectors come in. As you can see, we can create a feature vector for city A, which is, say, as you can see here, this one 130, that will be for city A, and then 33.93 and 86 if we consider inches and Fahrenheit. Similarly, for city B, we have this as a feature vector. And once we have these feature vectors for each of the cities, we can group them and put them in a stack in a array, a numpy array, as you can see here. So once we have this, each row represents a particular feature vector for that particular city. Now, why do we need feature vectors and how are they used? So what happens is, if we look at this particular figure here, we are trying to describe group the cities based on rainfall and temperature. Now, as we can see, city B is in a different group, which is yellow dots, and city A is in a different group, which are blue dots. What these features allow us to calculate mathematically are how close they are, how similar they are, and that helps us classify these data points into separate groups. Now, how do we know the points are close or they are similar? One way is by looking at distances between those 2 points, and other is we can take a dot product. So let's look at what dot products are and how vectors are involved in dot products. So in this figure we can see that there are two vectors A and there is a second vector B. Now, based on these vectors, we can calculate a dot product, which is given here on the left hand side by either of these two formulas. So for each of these dot vector, we have a magnitude, which is the length of the vector, and in this case the length of the vector is 5.65, which is calculated from this formula here, which is our Pythagoras formula. Now, these points, this is 0.4 and minus 4 and 4, and this point here is 2 and 2. So based on that, we can calculate the dot product between these two vectors A and B, and we get the value as 0. Now what a 0 value tells us is that those two vectors are orthogonal to each other, which means that they are perpendicular to each other. Now, what happens is, if similar to this, if we had other set of data points, which we'll see in next few slides, the numbers could be negative. What negative number tells us is that the vectors are moving in opposing directions, and if they are doing that, then it also could mean that they are not similar. So those data points should not be grouped together. And if they are moving in the same direction, the dot product, which is again a scalar number as we saw earlier, which was 0, then they are moving in the same direction, and hence we could possibly group them together as in one group. In this figure, on the right hand side there is a plot with multiple orange and blue dots. On the left hand side are two arrays, A and B. The array A is shown in the plot with blue dots. As you can see, this 0.11 is shown here. Then we have 0.50, which is shown here. And then we have 0.43, which is shown here, and so on and so forth. Similarly, the array B is shown here in orange dots, and we can see that -1, 1 is shown here, -5, 0 is shown here, and so on and so forth. Here we can also see that there are 2 points, -12, 12 and 12 and 12. They are shown there to show that they are orthogonal to each other, as we saw in the earlier slide, previous slide. Now, if we do a dot product of A and B, we get a matrix like this in Python. So you probably remember this from previous videos. To do a dot product, we use the NumPy library, and the notation is np.dot open parenthesis A comma B dot transpose. Now here the reason why transpose is there, because to calculate the dot product we have to multiply this one with this one, and then we have to multiply this one with this one. As we saw in this formula earlier, we are multiplying ax with bx and ay with by. And to do that, when we flip this, we can do a vectorized form of implementation where those two parameters, those two arrays can be used in the dot product. Now if we look at the second row in array B, when that particular those particular numbers are multiplied with the numbers in array B, we get this particular line here. What this tells us is that if we look at the direction of 0.50, vector at 0.50 and vector at -50, they are in opposite direction, and therefore we get a dot product that is negative. Similarly, the point -1 is again in negative direction, and hence we have negative. So all these values of dot products, that are the scalar values, are negative with respect to the vector here at 0.50. Now if we look at these arrows, if we look at this arrow for example now, and here we are looking at 0.43 and 0.50. So again 0.43, so we are 0.43 is the third one. So if we look in the third column, this is -20, so that is also negative. Now if we move this down to, let's say, 4.3 here, and then we come down here, so here now we have 4.3, and when we multiply with B, we would be looking at this particular row, and here we can see that the points minus 1 1, minus 5 0, minus 4, minus 3, those are negative, those have a negative dot product value, and that indicates that those are more than 90 degrees and they are moving in the opposite direction. On the other hand, if we look at 2 and 4.6, so if we look at this number right here, and if we look at the comparison of that particular vector with these vectors, then we can see a new set of values. Here with 1 1, which is right here, the values are positive. It means that those two vectors could be moving in somewhat similar direction, whereas the values for 5 minus 5 0 are negative. So this is much more obtuse angle between those two vectors, so they are likely moving in different directions. And whereas from other values we can see that number 31 is the highest, and 31 is for the point minus 1 and 4.89, which would be this point. And as you can see, higher the scalar values indicate that those two vectors would be moving in similar direction, and as we can see here, that is very clear because the angle between those two vectors is much smaller as compared to other vectors which had a negative scalar value, such as this one, where the angle between those two vectors was much larger. So that's the central idea behind how to interpret the dot product values between two vectors in this case. So what that also tells us is, from the machine learning standpoint, then we could consider those 2 points which have a higher scalar values are likely similar, and therefore those two could be grouped together as one group. Now let's move on to the next slide. On this particular slide, now we are looking at distances between 2 points, Euclidean distance. So this is another method that can be used to see if those two particular points are closer to each other or farther than each other. As you probably have guessed, if the points are closer, the distances between those 2 points will be smaller, and if the points are farther apart, then the distances between those 2 points would be much larger. As we can see on this plot, these are the same data points that we had in the previous plot, except that now we are going to focus only on the blue points, and among blue points only those 2 points that are shown here, which is 1 1 and 12, and these points are from our array A. So that's the first row and that's the last row from that array. And this we already talked, the smaller the number, the closer those data points are, and therefore it would help us classify those data points together if they are closer together. Now going back to that plot, we can calculate the distance between 2 points using this formula, which you probably already know, and here we get the distance of 15.56 between these 2 points, and in Python we can compute the same Euclidean distance, which I'll show in a little bit, where we can this array output here shows the Euclidean distance of points within the array A itself. So this is the distance from of point 1 1 from point 1 1 itself, that's why it's 0. And this is the distance of point 1 1 with 5 0, which is this 4.12. And similarly, this is the distance between point 1 1 and point 12 12. And this distance is same as what we calculated manually right here. So overall, as you have seen, that we can use these dot products and Euclidean distances to know if the points can be classified to be in a same group or they should be in a different group. Now I'm in Jupyter notebook, and I've already opened a new notebook and started working on this. So I've imported the library NumPy because we will need it right now as we are working with arrays. And here I've already created two arrays that we saw in the slides, A and B, with a few data points. Now what I'm going to show you is how to calculate the dot product and how to calculate the Euclidean distance between these two arrays. So let's go ahead and first calculate the dot product. Now to calculate the dot product, we need to use the transpose of B. The transpose of B would look something like this. So the way a dot product works is we are going to multiply. So let me create a cell here. So we are going to multiply 1 with -1 plus 1 with 1, and then multiply 1 with -5 and then plus 1 with 0, and so on and so forth. So np dot dot a b dot t, and this gives us the entire matrix for the dot product. As you can see, -1 into -1 is -1, plus 1 into 1 is 1, so -1 plus 1 0, and we get 0 values for these two as well, which are orthogonal vectors as we saw in the plots. So if you go back to the plot, so here as we can see, vectors -1 1 and 1 1, they lie on the same line, so these two are orthogonal, and the 12 -12 12 and 12 12, these two are orthogonal, and therefore we see those as zeros in this particular plot. Now the closest vector seems to be this number 46.8. So 46.8, so that would be, so we are looking at this row, which is this particular row from array A, and then we are looking at the last column, so we are looking last column here. So that's the dot product between those 2 points, 1.1 4.89 and -12 12. So if we look at that angle, it should be a smaller angle. So we are going to look at -1 1, which is this, and then we are going to look at this. So yes, as you can see, that angle 1.148, sorry, it's not this one, this angle. So as you can see, the angle between these two vectors is much smaller, and therefore the resulting scalar value of their dot product is larger and positive. Okay, Now let's look at how to calculate Euclidean distance. And there are two libraries that we can use to calculate the Euclidean distance. One is SciPy library, so let's import that library. So from SciPy spatial import distance, and then we write distance dot cdst a comma a. Now we are going to calculate the Euclidean distance of points only in the A array. Euclidean, and there you go. Now here there are a lot of decimal places, so we can round them off. So to do that, write around comma 2, and that will round it to 2 decimal places. So sorry, this should be np dot round. Okay, and there we see the 15.6 that we saw earlier in the slides. Next, we are going to look at another way in which we can calculate the Euclidean distance, and that's using the sklearn library. So let's go ahead and import the library from sklearn.matrix.pairwise import Euclidean distances, and then we can use the Euclidean distances AA to calculate the Euclidean distance. And again, the same way we can round the numbers. So let's do that. We round it to 2 decimals. Oh, sorry, np dot round. Okay, and as you can see, the numbers are same, so we get 15.6 in this case as well. That's it for this video. Hope you all enjoyed watching this video and learning about dot products, vectors, and the intuition behind why we do dot products, and why we calculate distances between the data points, and why it is important, and how it helps in machine learning, and how it helps in classifying data points together in different groups or the same group. In future, I'll also discuss eigenvalues and eigenvectors. That will be a separate video in itself. For this video, I just wanted to focus on dot products and Euclidean distances. I hope you have a better understanding of this now. I look forward to seeing you in future videos. Please like, share, and subscribe. It helps me stay motivated to get more content for you guys and make the videos more interesting. Thank you.